Welcome to Math 31. This is a continuation of lesson number 6 where we were looking at the derivatives of the sine and the cosine function. So we continue with that. Just do a few more examples of it and master some of the more complicated ones. Now, when you get something like this, f of x is equal to sine cubed x over 1 plus cos squared x, as you're watching this one, you can see probably that this is going to involve the quotient rule. So what I'm going to do first off is write this in a nice, easy to use method, which is highly advisable for these ones. So use brackets. This is equal to sine of x cubes, and this, the denominator, would be the cos of x squared. So I put it outside like that, so it's just easier for me to work with. Now I'm going to only do that when I need to, but I want it to always be perfectly clear when I'm solving this where the exponent, what the exponent belongs to. And then using the quotient rule, we would get u is equal to the sine of x to the 3. So u prime is equal to 3 sine of x to the 2 times the derivative of the inner. Now I'm going to go immediately to the derivative of sine x, which is cos x. So I'm not going to throw in the additional steps along the way. Then v is equal to 1 plus cos of x squared. So v prime is equal to 2 cos of x to the 1, which I won't bother writing, times the derivative of cos x, which is negative sine x. So I'm being really careful with this one. And that's what these trig derivatives are all about, being careful. Not difficult, because you've got simple derivatives, but you're constantly going back between cosine and sine, and as you see soon, even with other things, so you always have to watch out what's happening. So therefore, y prime is equal to u prime v minus u v prime all over v squared. So we sub in everything. Y prime is equal to u prime, so that's 3 times the sine of x squared times the cosine of x. I'm putting brackets around each one of them just for now, just to be careful. Liberal use of brackets is a good idea. If we don't need them, we can always take them off later on. Minus u, which is, 3 sine squared. See, in all my playing around, I forgot to put this. U prime v, which is 1 plus, I think I can salvage this one, cos x squared. So cos of x all squared. There we go. That's better. Minus u, which is sine x to the 3 times v prime, which is 2 times cos x, so, or negative 2 times cos x multiplied by sine x, all this over top of v squared. So that's going to be, in a big old bracket, 1 plus cos. I'm going to write this as cos squared x, because really that doesn't need to do anything more, and I'm not going to have to deal with that. So it's all squared. Now, anytime that you combine the quotient rule with the chain rule, such as we have done, you will have to factor out or take out a common factor. So in this case, if you take a look at carefully with each of the clusters, you will see that this first cluster has got sine squared x. So we can take out 2 of those because, so sine x to the 2. We can also take out, on the second cluster, we have sine x to the 3, so there's 3 sine x's plus another. There's actually 4 sine x's. So it can afford those 2. And we can also take out a cos x. And then that's going to leave us with, in the big bracket, a factor of 3. And all we have left is 1 plus cos squared x. I guess we can write it like that now. And then the minus times a minus is going to give you a plus 2. Now the cos x has been divided out, and we had 4 sine x's, so now we have 2 left. So 2 plus 2 sine squared x. And then over that denominator, which is 1 plus cosine squared x all to the 2. So I'm going to get a little more space for this one. And what I'm going to do next is to clean up the inside of the bracket. I'm going to distribute that 3 in and then see what we get. So y prime is equal to sine of x squared. Now you could certainly write that as sine squared x because it's not going to be an issue anymore, multiplied by cos x. And when we distribute that in, we'll get 3 plus 3 cos squared x, and then we've got the plus 2 sine squared x. And then this is all over top of 1 plus cos squared x to the 2. Now you're thinking, well, we're done. And you could argue that you are. However, most answer keys will want you to go a little bit further because we have cos squared x and we have sine squared x, and there's a very clear relationship between the two. You can change cos squared into sine squared, or you can change sine squared into cos squared. Now both are correct. So there's really, at this point, it's just a choice. But just to keep things interesting, I'm going to convert sine squared into cos squared, because using that Pythagorean identity, sine squared x is equal to 1 minus cos squared x. So I'm going to do that. That will give me y prime is equal to sine squared x, I'm going to write it back in that form, times cos x, and then multiplied by 3 plus 3 cos squared x plus 2 times 1 minus cos squared x. So a reminder, I chose to convert this into cosine, but it could have been the reverse. And the problem that you run into with that was with answer keys, and it's pretty much unavoidable unless there's one that makes a lot more sense than the other. But with your answer key, you've got to be prepared to compare your answer and see, well, is mine the same thing or not? It's unfortunate, but there's just no way to get around it. Now, when this 2 gets distributed in, that's going to be 2 minus 2 cos squared x. And I'm just going to write it up top so that I can now get my like terms together. dy dx is equal to sine squared x times cos x multiplied by, well, 3 plus 2 is 5, and then 3 cos squared x minus 2 is cos squared x is plus cos squared x. And then all over top of 1 plus cos squared x to the 2. So it's not pretty, but it's correct. And there doesn't appear to be any other cancellations we can do for that one, so we just leave it the way it is. So all the regular things, such as product rule, quotient rule, whatever, apply with these, and you've got to get good at them all. But it's all about being careful with them. Nothing difficult in what we did, but there's lots of potential for confusion. Now this one, another problem. Now this is actually a bracket. I don't know why that got cut off. Cosine of sine 2x squared minus 1. So what's happening here is the argument of cosine is sine 2x squared minus 1, and then the argument of the sine function is 2x squared minus 1. So we have a function within a function, and we have to, within a function actually, and we have to make sense of this one. So this is really a chain rule problem from the get-go, but my advice for you on this problem would be to use a substitution like we were doing earlier. You can never go wrong with making a substitution. You may be throwing in a few extra steps when it's not necessary, but it's never wrong to do so. And here the choice is what we let u be equal to. Now what I'm going to do is make it the biggest thing I can, which is u is equal to sine of 2x squared minus 1. The question you're probably asking yourself, what if I made u equal to 2x squared minus 1? Then I would have had y is equal to cosine of the sine of u. And it's actually quite manageable. So if you've done that, you're okay. So don't worry excessively about what I should make the substitution for, because you have more than one choice. Normally you try to make it as big as possible. So I'm making it for the argument of cos, because what I want this to look like, and which it will, would be y is equal to the cosine of u, which is very easy to differentiate. And otherwise it would have been the cosine of the sine of u. But that isn't really a huge problem. So one way or the other, you're going to have to differentiate all parts of it. So it really doesn't make a lot of difference. Now when we differentiate this u, and notice I'm going to write it as du dx. I'm not going to go u prime because I really want to make sure I know what's going on with this one and with respect to which variable. Because the derivative of sine is the cosine of 2x squared minus 1. But this is going to be multiplied by the derivative of the inner. And I'm going to go there directly, which is 4x. So du dx is equal to 4x times cosine of 2x squared minus 1. Now I start the differentiation with the main problem. So dy dx is equal to the derivative of this function, cosine u, which is negative sine u, multiplied by the derivative of u with respect to x. That's a u, just like we always do. Now, make our substitutions in, because we've got that conveniently worked out over to the right of the screen. So this is negative sine u. Now I'll make the substitution in for u afterwards. This is multiplied by 4x times the cosine of 2x squared minus 1. And here's where things get interesting. We now make our substitutions in, and dy dx is equal to negative sine of u. Well, u is sine of 2x squared minus 1, so this really is the sine of sine 2x squared minus 1. So I'm introducing a square bracket just so I can keep it clear what's going on. The sine of the sine. It's not wrong. And multiplied by all this. Now I'm going to take this cosine of 2x squared minus 1. And 4x should be written in the front anyway. So I'll put that 4x in the front, and then I'll put a negative there, if you can read that. And so I'll rewrite that just to make sure that there's no real problem with it. So dy dx is equal to negative 4x cosine of 2x squared minus 1. So I'm putting that 1 in front, doesn't really matter, multiplied by the sine of the sine of 2x squared minus 1, like that. Not really difficult, but it's a matter of keeping it real clean and using a substitution where you can. Really recommend it. Now let's go on to a couple other things that might be of interest. Naturally, you can get implicit differentiation. And with implicit differentiation, particularly when you've got them like this, x times sine y, y sine x, you're going to have to use the product rule to work both of those ones out. Now, I'm not going to show the product rule for these ones because they're simple, and I don't want to throw in anything more than I need to. Product rule, of course, does say you take the derivative of one and then you leave the others. So the derivative of x is 1 times sine y, and then plus the x stays the way it is, multiplied by the derivative of sine y. Now the derivative of sine y is cosine y multiplied by the derivative of the inner, which is y prime. So I'm using little prime notation like this just to keep it as tidy as I can. Then when you break up this one or differentiate that one, the derivative of y is y prime. The sine x stays as is. And then the second one, the y stays the way it is, and the derivative of sine x is cosine x. And then because the argument is just x, we don't have to do anything more. And that's equal to 0. Now, as always, we gather up the terms that have a y prime, like this, y prime sine x. Take the other ones to the other side, so we get negative sine y when that first term comes over, minus y cos x, like that. Do what we've always done, factor out a y prime, and that leaves you with x cos y plus sine x, and that's equal to negative, I'll factor out a negative, so I get sine y plus y cos x, and then we divide out. So y prime is equal to negative sine y plus y cos x, all divided by x cos y plus sine x. See if there's any obvious mistakes that you've made with it, or I've made with it, I guess. And it looks good. Now let's move away from some of these problems where where you're dealing with straight differentiation and take a look at some of the applications of these. So find the equation of the tangent line to the curve f at x is equal to sine x at 0, 0. Now this problem doesn't break a lot of new ground. We've done dozens of these before. But to get the equation of the tangent line, you have to remember, of course, that is the derivative. So really what you're trying to do is find f prime at x, because that will represent the slope of the tangent line to that curve. So if f at x is equal to sine x, f prime at x is equal to cos x. And it's at this point 0, 0. So there's your x value. So really what you want to do is find f prime at 1. So because we want to find the slope of the tangent line at x is equal to 0. Or x equals 0. So why did I write 1? Okay, f prime at 0, excuse me. So f prime at 0 is equal to the cosine of 0. So f prime at 0, well, the cosine of 0 rads is going to be equal to 1. So therefore, m is equal to 1. And this is through the point 0, 0. So y is equal to mx plus b, because we want the full equation. So 0 is equal to 1 times, well, x is 0 plus b. So b is equal to 0. And that would mean that our equation is y is equal to 1x plus 0. Just like that. Now, the next, on your notes, we've got a few more questions. We might as well get those taken care of right away. We want to get on the next one, find the equation of the tangent to the equation of the tangent to this function, a little more complicated, at x is equal to 3 pi over 2. So, to solve this one, we basically launch into it the same way we always did before. So y is equal to this. So really what we want is dy dx. So we need to get the slope, we need to get the derivative, and more specifically, we want to get it at x equals 3 pi over 2. We do not have a y value. So dy dx, the derivative is 1 of x is 1, and then the derivative of cos x is minus sine x. And if we can get dy dx using this notation, Leibniz notation, at x is equal to 3 pi over 2. And we substitute in the value, and we get 1 minus the sine of 3 pi over 2. Well, you have to know what the sine of 3 pi over 2 is, but that is knowable. So dy dx at x is equal to 3 pi over 2 is equal to 1 minus, well, the sine of 3 pi over 2 is negative 1, so 1 plus 1 is equal to 2. So therefore, the m is equal to 2, the slope of the tangent line at x is equal to 3 pi over 2. Now, in order to get the y coordinate, we're going to have to find out what the y value is on the original. So we need to find the y coordinate. So make sure you go right back into the original, and you'll get y is equal to x, which is 3 pi over 2, plus the cosine of 3 pi over 2. Now, the cosine of 3 pi over 2, if you take a look at your unit circle, is 0. So y is equal to 3 pi over 2. So really what we want is the equation of the tangent line where the m is equal to 2 through the point x is 3 pi over 2, and y happens to also be 3 pi over 2. And we go into y is equal to mx plus b. So 3 pi over 2 is your y value, and that's equal to m, which is 2, times 3 pi over 2, which is your x, plus b. So we get 3 pi over 2. 2 times 3 pi over 2. Now I know you normally would cancel the 2's out, but I'm going to write that as 6 pi over 2 because I see that I want to get a common denominator with this. And when I isolate the b, I will get 3 pi over 2 minus 6 pi over 2. So that's minus 3 pi over 2. So we have a lot of 3 pi over 2's around here. And then the equation, therefore, is going to be y is equal to m, which is 2, x minus 3 pi over 2. There's the equation of the tangent line. So that's how these ones go. Now the last question is well, actually let's take a look at this one first. Here's what the graph looks like of that function. So if you key that into your calculator properly, make sure you're in rad mode. You may not get as nice a scale as I got. And we want to get the equation of that line right there at 3 pi over 2. So that seems reasonable. The slope could be 2. It's a little tough to tell when you've got rads on the x-axis. But it looks good. So these functions that are the combined function between a linear graph and a trig graph do not look like a linear graph or even a trig graph exactly. Now the last question is this: find the absolute max and min values of this function in this interval. So you may want to stop and do this one on your own. It's not that difficult of a question. You're given a specific interval, and I'm going to do the math first, and then I'm going to take a look at the graph for it afterwards. And we don't need to worry about the domain unless there's any gaps between 0 and 3 pi over 4, which there are not. Cos and sine graphs are continuous functions, so we don't need to worry about that. The domain is given. Want to remind you, though, when you're dealing with absolute max and mins, you don't need to do what we have been doing before, like getting the first derivative analysis or second derivative analysis or anything like that, because you just need to compare the points, the endpoints and the critical numbers, and that's good enough. So we get the derivative f prime at x is equal to the derivative of cos 2x, which is negative sine 2x multiplied by the derivative of the inner, which is 2. And then plus 2 sine x is plus 2 cos x. So in a cleaner form, f prime at x is equal to, well, let's write that 2 cos x in front. 2 cos x minus 2 sine 2x. I think I've got it all there. Now, when you look at this, you now, without thinking anymore, you think critical numbers, which is correct. We do need to get the critical number or numbers between 0 and 3 pi over 4. Now, those occur where the first derivative is equal to 0, principally, or where it doesn't exist. But I'll start with the 0, 2 cos x minus 2 sine 2x. Now, what I would recommend in a case like this is that you divide out a factor of 2, just to make things a little bit easier, because it's divide the 0, the left side, by 2 as well, and you get cos x minus sine of 2x. And you've got choices with this one, really, in terms of location, where you put the sine 2x. But if you use a double angle formula with this one, you'll get cos x minus, now put a big bracket up because you don't want to make a mistake on the sign, but sine 2x is 2 sine x cos x. And then 0 is equal to cos x minus 2 sine x cos x. And when we, the bracket, of course, in this case didn't really make a difference because there's no addition with it, but make sure that you do that just for safety's sake. Take out a factor of cos x. We've seen this before, sort of thing before. So 0 is equal to the cosine of x multiplied by 1 minus 2 sine x. We set them both to 0. So cos x is equal to 0. Ask yourself where that is true. And cosine is equal, x is equal to 0 at pi over 2 and at 3 pi over 2, using the unit circle or what you know about cosine. Now, the issue with that is that we have this restricted domain. Now, 3 pi over 2 is 3 pi over 4 is the endpoint, so 3 pi over 2 is outside the domain. No sense even playing around with that. And then 1 minus 2 sine x would be equal to 0. So 0 is equal to 1 minus 2 sine x. So 2 sine x, bring it over, is equal to 1. Sine x is equal to 1 over 2. So this is going to normally put you in quadrants 1 and 2, where sine is positive. Just get a little bit of space here. The reference angle is pi over 6. We know that special angle. So without even drawing it, in quadrant 1 we have pi over 6. Quadrant 2 we have 5 pi over 6. Well, 5 pi over 6 is also outside of the domain. We don't get to keep it. So really we just have two critical numbers within this domain. Bring up a new, get some space to work these ones out. And all we do now, instead of doing the analysis on it, is we compare the endpoints and the critical numbers. So we need to compare f at 0, we need to compare f at pi over 6, f at pi over 2, and f at 3 pi over 4. And then see what all we want, the absolute max and the absolute min. So f at 0, if we plug in 0 to the original function, make sure, that becomes the cosine of 2 times 0 plus 2 sine 0. Well, cosine of 0 plus 2 times the sine of 0. Cosine of 0 is 1. Sine of 0 is 0. So f at 0 is just equal to 1. So we file that away. We make sure we see that. And then we go on to the next one. I'm going smallest to biggest. So f at pi over 6 is equal to the cosine of 2 times pi over 6 plus 2 times the sine of pi over 6. So this is equal to the cosine of pi over 3 plus 2 times the sine of pi over 6. Cosine of pi over 3 is 1/2. We know that number. And the sine of pi over 6 is 1/2 as well. So this becomes 1/2 plus 1. So that, I'm going to write that as 3 over 2. So that's f at pi over 6. Nice clean number. So far we've been very fortunate with this one. Then we go on to the next one, which is f at pi over 2. So f at pi over 2 is equal to the cosine of 2 times pi over 2 plus 2 times the sine of pi over 2. Now that's equal to the cosine of pi plus 2 times the sine of pi over 2. Now the cosine of pi is -1 plus 2 times sine of pi over 2, which is that's -1 plus 2 times 1. And that would give us -1 plus 2 is equal to 1. So f at pi over 2 is equal to 1. And then to finish it off, f at 3 pi over 4, this is the other endpoint, is equal to cos of 2 times 3 pi over 4 plus 2 times the sine of 3 pi over 4. So this is equal to cosine of 3 pi over 2 plus 2 times the sine of 3 pi over 4. Now that's 0, 3 pi over 2, cos of that, plus 2 times, well, 3 pi over 4, it's quadrant 2, it's positive, so it's root 2 over 2, and that is actually equal to then square root 2. And now all we have to do is compare. Now root 2 is about 1.4. So the absolute max is going to be, and I'll write this out in the next when I get some space, is going to be 3 over 2. The absolute min, the smallest number we have is 1s and 1s. I guess is going to be 1. So here's a min, and I think we have a min there. So let's take a look at the graph, and then we can see that even by inspection this is supported. The absolute max is 3 over 2 at x equal pi over 6. Very apparent from this graph. The absolute min is at 1 at x equals 0 and x equal pi over 2. So it works the regular way. So it's been kind of a long lesson. I'm going to stop right there, and then we'll get on to the derivatives of the other trigonometric functions. Thank you for your time.